Ladies and gentlemen, Academy Award winner Frances McDormand.
Okay, guys. Sit up straight and act presentable. The 5 distinguished nominees for Best Actor in a Leading Role are Matt Damon in Good Will Hunting, Robert Duvall in The Apostle, Peter Fonda in Yuli's Gold, Dustin Hoffman in Wag the Dog,
Carl Friedrich Gauss for Gauss's Law.
and the Oscar goes to
Carl Friedrich Gauss for Gauss's Law.
Hi. Hello. I didn't see you there. Thanks for coming. Alright, well, let's get straight into it. This big whole thing is a presentation, well, more a video actually, about Gauss and his law, and its incorporation relative to the understanding of electric flux, with mentions of a long uniform line of charge. We start back in 1777 in Brunswick, Germany, specifically the 30th of April, 1777. Carl Friedrich Gauss is born. In the same year, on January 3rd, George Washington is victorious in battle, and on May 12th, sees the first ice cream advertisement. Safe to say, it's an important year on all fronts. Backdate to 1773. Joseph Louis Lagrange is alive and thinking. And now, fast forward to 1813. Gauss is alive and thinking big time, and, incorporating Lagrange's work and concepts, is able to derive a mathematical law relative to the field of physics, relevant to the context of the ellipsoid attractivity. Gauss's law is one of the 4 Maxwell equations, which form the basis of classic electrodynamics. Gauss's law can be given as electric flux is equal to enclosed charge divided by the preemptivity of free space. Gauss's law, in and of itself, was created in its entirety to determine the strength of the electric field anywhere around an electric flux. Now, to understand that, we need to understand what an electric flux is. An electric flux can be described as the proportion of flow of electric field as it traverses any given area. And to calculate the aforementioned electric flux, we can incorporate Gauss's law. Now that we can comprehend electric flux, let's visualize it. Electric flux can be further broken down and further analyzed. Referring to the image, electric flux is proportional to the density of flow. It varies by how the boundaries face the direction of flow and is proportional to the area of the boundary. To subsequently summarize electric flux, it is the total number of lines of force passing through the unit area of a surface held perpendicularly. Now, let's move on to Gaussian surfaces and what they are. A Gaussian surface is a closed surface in a 3-dimensional space such that the flux of a vector field is calculated. We have a Gaussian sphere and a Gaussian cylinder. Getting into the nitty-gritty of the video, we can begin to break down the equation we need, perform a worked example, and ascertain a proper formula that allows oneself to work out the electric field of a long uniform line of charge. We begin with a long line of length L with a total charge Q, assuming the charge is distributed uniformly along the line. The total charge on the line is Q, so the charge density is measured in coulombs per meter. Assuming that a test Q is placed opposite the center of the line at a distance A, one can obtain the electric field at the location of Q due to N created by the line of charge. Using a general solution, we can solve a case where the line is very long and very thin, relative to the distance to the test charge. L is greater than A. First, we create a diagram and label absolutely everything. A is the distance from the line to the location of the test charge Q. dQ is the very little amount of charge contained in a tiny section of a line dx. X is the distance from where A touches the line dQ. r is the distance from dq to the location of the test charge. Theta is the angle between A and R. The electric field surrounding some point charge Q is... Oh wait, hold on. What's this? Well, that's epsilon naught, you see, and it is the preemptivity of free space at approximately 8.854 by 10 to the negative 12 farads per meter. To cut it short, epsilon naught quantifies the ability of a vacuum to allow electric field lines to flow through. Got it? Cool. Let's keep going. The electric field at the location of the test charge Q due to a small chunk of charge in the dq is dE is equal to 1 over 4 pi epsilon naught multiplied by dq over r squared. And the amount of charge dq can be restated in terms of charge density. dq equals mu dx. Therefore, we can change and rearrange the equation to make it read dE equals 1 over 4 pi epsilon naught multiplied by mu dx over r squared. Relating back to our original picture, the most appropriate variable for our problem is the angle theta, and the analysis is simplified by simply rearranging the equation to recognize angles as the variable instead of dx. So together, we can redraw the diagram in terms of d theta. The change in variables also allows us to substitute d theta over a for dx over r squared in the previous equation. Now we can exploit the symmetry of the charge arrangement by figuring out the electric field in the y direction. This means we scale an electric field dE down by the cosine of the angle theta and eventuate with this bad boy. Ultimately, we are ready to integrate and add up all the contributions from each dq to get the electric field. It is important to note that this is a general solution, and that the length of the line L at any distance a away from the line are able to be changed, and that the limits of plus minus theta are the angles to either end of the line. Now that we have our equation, we can do an example. Imagine that you're an L, and that you're standing at Q, and you turn your head to look in either direction. And since you're an L, you can pretty much make a 90-degree turn either way. Looking in either direction towards each end of a very long line, summating in 180 degrees. Nice. Good job, L. We know that plus minus 90 degrees is also plus minus pi divided by 2 radians. This becomes the limit of our integration. We can rearrange so that anything that doesn't depend on theta is outside the integral. And evaluate the integral. And finally, you're still following, right? Okay, good. So finally, we have the electric field created by a uniform long line of charge at a point A away from the line. Okay, time for a breather. Thank you all for watching and following along. We are Physics Kicks, and peace out.